Okay, so in the final few lectures of this course, we'll be looking at the singular value decomposition, which is probably the most important tool in applied linear algebra. And it's what we've been building up to in this course. Okay, so one of the main goals of this course is to factorize or factor a matrix. Okay, and two techniques we've seen is diagonalization and orthogonal diagonalization. Okay, for diagonalization, we have A equals PDP inverse, where P is invertible and D is diagonal. And for orthogonal diagonalization, which is a specialized form of diagonalization, we instead have Q orthogonal, right? And D still diagonal. Okay, so this orthogonal diagonalization was sort of the best form we could get. Okay, but it only works for a very special kind of matrix, right? It only works for symmetric matrices and nothing else. So our more generalized diagonalization, it works for more matrices, okay? But it still only works for square matrices, okay? So in total, these two techniques are good, but it's really restricted in where it succeeds, right? It only sometimes works for square matrices, right? And there are a lot of square matrices it doesn't work for. So what we want to come up with is, or the idea is to maybe loosen some of the restrictions that we have here and get a factorization that is like diagonalization, but always works for any size matrix, okay? Not just square matrices, but, rectangular matrices that are non-square as well. Okay, so that's a lofty goal considering how sort of finicky diagonalization is, but that's our goal now. Okay, so the immediate problem is that diagonalization was always in terms of an eigenvector matrix P or Q and an eigenvalue matrix D, right? But eigenvalues and eigenvectors are only defined for square matrices, right? It doesn't make sense to talk about eigenvectors and eigenvalues for non-square matrices. Okay? So we're going to need a new idea. Okay, the new idea will be singular vectors and singular values. Okay, so if you remember back to, I think, lecture 7, we had a diagram like this, right, where we studied the subspaces involved in a rectangular matrix, right? So if we have m rows and n columns, then the action of multiplying a times x, right, where x is in Rn, and then the product is in Rm, gave us subspaces like this. Okay, we got the row space and the null space in Rn. Okay, and now we know, in fact, that drawing it like this is correct because these two spaces are perpendicular, they're orthogonal complements. Okay. And then we have the column space over here, and I've added in another subspace. Okay, so the other subspace, or the orthogonal complement of the column space in A, is actually the null space of A transpose. Okay, so it serves the role of the null space of A over here. It's the null space of A transpose. Okay, and it is the orthogonal complement of the column space of A. Okay, and so by the rank nullity theorem, we have these two equations where n, right, equals the dimension of the row space, of course that's equal to the rank of A, plus the dimension of the null space A. Okay, that's just directly the rank nullity theorem. And you can apply the rank nullity theorem over here as well. Okay, so M of Rm is equal to the dimension of the column space A, equal to the rank of A, plus the dimension of this new space here, the null space of A transpose. So the reason why we've returned to this picture is because if we're going to have something that's going to replace eigenvectors and eigenvalues, we're going to have to think about both of these spaces instead of just Rn. To think about both of them. Okay, so like I said, if m is not equal to n, which is what we're assuming here, then the eigenvector equation isn't going to make any sense, because that would require x to be both in Rn and Rm, which is impossible since they're different spaces. Okay, so I guess a natural thing we could try to do is change this equation so that x, or x is a vector that lives in Rn, and instead of x over here, we have a vector that lives in Rm. So instead of an eigenvector, we'll have a pair of vectors, and we'll have some number connecting them. So that's the idea for singular values and singular vectors. Okay. So instead of a single x, we're going to look for a pair of vectors, v and u, and some number, sigma, such that AV equals sigma u, okay, where v lives in Rn over here, and u lives in Rm over here. Okay, and we're going to call v the left singular vector. We're going to call u the right singular vector, because v is on the left side of this equation and u is on the right side. And we're going to call sigma the singular value associated to the pair vu, right? It's going to be a number that makes this equation true. Okay, so if we want to emulate what we did with diagonalization, we're going to want to find an orthonormal basis for Rn made of left singular vectors, and an orthonormal basis of Rm made of right singular vectors. Okay. So remember, with regular diagonalization, we looked for n many eigenvectors that were a basis for Rn. And with orthogonal diagonalization, we looked for n many orthonormal eigenvectors that were a basis for Rn. Okay. Now we have two subspaces to take care of, Rn and Rm. Okay. And we want our basis for Rn to draw from the set of left singular vectors, so that's why we're calling them v's. And we want our basis for Rm to be right singular vectors. That's why we call them u's. So we don't have eigenvectors to work with now. So how can we sort of set up these bases, or think about these bases? Okay. So remember, if A is m by n, and we have rank R, then we have the following in Rn. Okay. So we have let me just quickly show the picture. Right, this is Rn, and the two subspaces we have inside Rn are the row space of A and the null space of A. both subspaces associated to A. Okay, and the dimension of the row space of A is going to be R, the rank of A. The dimension of the null space of A is going to be n minus R by the rank nullity theorem. Okay. So if we're looking for V1 or Vn, we can say that the first 1 through R vectors can be a basis for the row space, and the last n minus R vectors, so the indices will be R plus 1 all the way up to n, will be a basis for the null space. Okay, that's how we'll split up the dimensions. That's how we'll index it. Okay, and you may ask, well, if we just take the union of these two sets, is that still, or is that an orthonormal basis for the whole thing, Rn? Yes, because these two subspaces are orthogonal complements. That means they're a direct sum, right? And so all of these vectors will be orthogonal to all these vectors, and altogether they will be orthogonal and independent and of unit length, and so they will be an orthonormal basis for Rn. Okay, so that's one way to think about how we can split up the orthonormal basis for Rn. Okay. And a very similar thing for Rm. Okay, so let me just show the picture again. This is over here. And the two important subspaces are the column space and the null space of A transpose. Okay. Very similar setup. Okay, so the dimension of the column space is R. Dimension of the null space of A transpose is M minus R. Okay, and we're looking for an orthonormal basis of Rm. So the first R vectors will be from, will be the basis of the column space, and the remaining M minus R vectors will be the basis of the null space of A transpose. And since they are orthogonal complements, when we put those two sets together, that forms an orthonormal basis for Rm. Okay. So if we divide up our basis for Rn like this, okay, into basis for the row space and basis for the null space. And if we divide up our basis for Rm like this, basis for the column space for the first R, and basis for the null space of A transpose for the final vectors, okay, we can now ask, what would it mean for these V's and these U's to be singular vectors of A? Okay. What are the relationships we'll need? Okay, so these are the relationships we'll need. Okay, we'll need that A times V1 equals sigma 1 U1. A times V2 equals sigma 2 U2. All the way down to A times VR equals sigma R UR. Okay, so we have two bases for these two spaces, and we're just saying, what if they were singular values? Well, then they would have to satisfy these. Okay. For the remainder, we're getting into the basis of the null space. Okay, so A times VR plus 1, so VR plus 1 is inside the null space, is just going to equal 0 on the other side. Okay, since it's in the null space. And the same for the rest of these. Okay, so that's how we're going to write the relationship for the rest of the V's when R is or for r plus 1 to n, like this. Okay, so that's why we divided it up, so we can just write these as zeros right away. Okay, so ultimately we want a matrix factorization. So we're going to translate all these relationships into a matrix equation that looks like this. Okay, so we're going to write A, that comes from the A's over here, times a new matrix. We're going to call it V, okay, and it's going to be n by n orthogonal. Okay. Right, since we're assuming the V's are orthonormal, this will be a n by n orthogonal matrix. Okay. That comes from these guys here, and it's going to equal U, an m by m orthogonal matrix. Okay, and if we want this to equal the right hand side here, okay, we're going to need to scale each of the columns here by the appropriate sigma, or by 0. Okay, and so to do that, we need a matrix that looks like this. Okay, so this matrix, so this is capital sigma here. Over here, these are lowercase sigmas. Okay, so we're going to collect our small sigmas and put them into a diagonal matrix in the top left corner here. Okay, and we're going to fill in the rest of the matrix with zeros. Okay, so sigma is going to be the same size as A. It's going to be an m by n matrix. Okay, but we're going to have R, where R is the rank, many little sigmas on the diagonal. Okay, so I write diagonal matrix in quotes here because, right, this isn't a true diagonal matrix because it's not square, right? But it only has non-zero entries on its diagonal, its main diagonal. So that's why it's sort of a diagonal matrix. Okay, so now we have this equation, and now I'll write it as AV equals U sigma. Okay, and now since V is orthogonal, that means it's invertible. Okay, and that means I can rearrange this equation to isolate for A, right? So I have A equals U sigma V transpose. So this is the singular value decomposition. Okay, A is equal to an orthogonal matrix, an m by m orthogonal matrix, U, times a sort of diagonal matrix. Again, not a true diagonal matrix, but only has non-zero entries on its diagonal, times an orthogonal matrix. Okay, so how this differs from, say, orthogonal diagonalization is, well, this isn't really a diagonal matrix, and these two orthogonal matrices aren't directly related. Okay, we're not taking U transpose at the end, we're taking V transpose, another matrix, right? And the U and the V, unless A is square, are going to be different sizes, right? The U is m by m, and the V is n by n. So it's a different sort of decomposition than diagonalization, but it has a lot of the same features. Okay, so what I've said so far is just a template of how this decomposition sort of works in theory. Okay, but if I were to just like remember, the row space and the column space, right? They're subspaces, so they have an orthonormal basis, right? But they have infinitely many orthonormal bases, right? If I were to just compute a basis for this, the row space and the column space at random, they probably won't satisfy these conditions. So what I've said so far just works in theory. What we want to do now is determine how to choose the V's, U's, and sigmas so that it's guaranteed to work. Okay? And we want to come up with a method so that it will always work. So we've come up with the template for the singular value decomposition. Okay, we have A equals U sigma V transpose, where U is m by m orthogonal, V is n by n orthogonal, and sigma is m by n, and it has a sort of diagonal formation. Okay. So the main question is, how do we find the U's, V's, and the sigmas that will make this true, make this equality true? Okay, and in the previous section, we showed that it's helpful to sort of chop up the basis for Rm and Rn into the basis for the null space, or the null space of A transpose, and the basis of the column space and the row space, which are the U1 through UR and the V1 through VR. Okay, so we don't have a square matrix A to find eigenvalues of, so we're going to look at two square matrices that are associated to A that we can look at the eigenvalues of. Okay. So we've seen these matrices before in our work with projection and least squares, right? We've seen A transpose A and AA transpose before. Okay, so both of these are symmetric matrices, right? So we're going to look at these matrices. So we're going to assume that we have this factorization in hand. Okay, so if we have this factorization in hand, what does that say about these two matrices here? That's going to be our question. Okay, so if A has this factorization, and that means that A transpose looks like this when you take the transpose of both sides. So let's look at what it says about A transpose A. So if I write A transpose like this, and I just write A beside it like this, I get this expression. I get U transpose times U in the middle. And since U is orthogonal, that means this just becomes the m by m identity. Right, so that part just goes away, and then I just get this expression. A times A transpose is very similar, okay? Except now I get V transpose V in the middle. That becomes the n by n identity, and I get this expression. Okay, so should look at these matrices in the middle. Okay, so sigma transpose sigma, that's going to be an n by n matrix. Okay, and if you think about what it has to look like, it will be diagonal, right? Like a true diagonal matrix, because it will be square, n by n. And on its diagonal, it will have sigma 1 squared, sigma 2 squared, all the way down to sigma r squared. Okay, so it'll have those numbers on the diagonal. Okay. Similarly, for sigma transpose, it will become an m by m diagonal matrix with those same numbers on the first r entries of the diagonal. Okay, so remember that these two matrices are symmetric matrices, right? And look at what we've done when we've written it like this. We've written it as orthogonal times diagonal times orthogonal. Orthogonal times diagonal times orthogonal transpose, right? That means that these expressions are the orthogonal diagonalizations of A transpose A and A transpose, respectively. Okay, remember, they're symmetric matrices, so they can be orthogonally diagonalized. Okay, and any factorization of the form orthogonal, diagonal, and then orthogonal transpose must be an orthogonal diagonalization of those matrices. Okay, so we found an orthogonal diagonalization of those matrices. Okay, what does that tell us about the V's and the sigmas? Okay, so what this equation is saying is that since we have orthogonal, diagonal, orthogonal transpose, the columns of V are going to be the eigenvectors of A transpose A, right? And the entries on the diagonal of sigma transpose sigma are going to be the eigenvalues of A transpose A. Okay, so the question of where we get our V's and our sigmas is starting to be clear now, right? So the first V1 through VR eigenvectors, okay, of A transpose A will have eigenvalues sigma 1 squared through sigma r squared. If it happens that n is greater than r, then we'll have a few more v vectors left over, and these will be eigenvectors of the eigenvalue 0. Okay. And so this is the eigenvalue eigenvector expression in terms of the v's and sigmas that we're looking for. Okay, and we can do the exact same analysis for A transpose. Okay, so this is the orthogonal diagonalization of A transpose. So the U's, the columns of U, are eigenvectors of A transpose. The first R many eigenvectors have eigenvalues sigma 1 squared through sigma r squared. Okay. Again, if m is greater than r, then the leftover u's will be eigenvectors associated to 0. Okay. So what does all this mean? Okay. Remember, we're looking for these u's, v's, and sigmas that will make our SVD work, right? So this is telling us where to find those u's, v's, and sigmas. Okay, they're hidden in these matrices. Okay, so let's observe that A transpose A and A times A transpose have the same non-zero eigenvalues. Okay, this set, sigma 1 squared all the way up to sigma r squared. They share those non-zero eigenvalues. Okay. Also note that A transpose A and A times A transpose are even better than just symmetric. They're positive semi-definite. Okay, so it's not difficult to prove that these are positive semi-definite. Essentially, the solution to assignment 3 question 2 if you just take it one step further, we'll show this fact. Okay, so that means that the eigenvalues are positive and real. Okay, yeah, these eigenvalues here are positive and real. Okay. So looking at these two matrices gives us a way to choose our U's, V's, and sigmas that'll make this decomposition make sense. Okay, and I should add that these two matrices share the same non-zero eigenvalues, but depending on their sizes, one of them could have 0 and the other one could not, or they could both have 0, or neither could have 0. Okay, so 0 could be floating around in the eigenvalues of these matrices, but for these important eigenvalues, the non-zero ones that are positive, they will be the same between these two matrices. Okay, so now we've said enough to state the formal theorem of the singular value decomposition. Okay, so we assume A is a real m by n matrix, then the decomposition of A involves an m by n diagonal matrix sigma of this form, okay, where we have a diagonal matrix in the top left corner and the rest is filled with zeros. Okay, so here's a full statement. Right? If A is an m by n matrix with rank R, then there exists a sigma like this, which have diagonal entries. The first R diagonal entries are the first R singular values of A. Okay, so the R singular values are these numbers, and we can order them like this because we know they're real numbers, and so they can be ordered. Right? If they were possibly complex numbers, we wouldn't be able to order them like this. Okay? And we also know they're positive, right? So we know that they're the non-zero ones are greater than 0. And like before, we have an m by n orthogonal matrix U and an n by n orthogonal matrix V that complete the factorization like this. Okay, so that's statement of the theorem that these things do exist. Okay, and here is a sort of algorithm to actually do it for a given A. Okay, so we want to investigate the matrix A transpose A, right? So the first step is to orthogonally diagonalize A transpose A. Okay, and when you do that, you'll get orthonormal eigenvectors v1 through vn. Okay, and these are its eigenvalues, right? We can order them like this. Okay. And now for step 2, we're going to use the information from step 1 to construct the matrix V and the matrix sigma, right? We construct V just by putting V1 through Vn as the columns, and we construct the diagonal matrix sigma by putting sigma 1 through sigma r on the first R diagonal columns, first R diagonal entries, and we set the rest of the entries equal to 0. Okay. Okay, so we have our V's and we have our sigmas. We need to find the U's. Okay, so we're going to use this relation here. Okay, A times V1 equals sigma 1 times U1. Okay, we need that relation to hold. Okay. Since we already know the V's, we can get the UI's, or the first 1 through R UI's, using this relation. Okay, so U1 through UR can be determined by this relationship here. If M is greater than R, then we'll have some extra vectors that we need to compute. UR plus 1 through UM. Okay, and how we do that is by looking at the span of U1 through UR, okay, and then computing the orthogonal complement of that span. Okay, so we know how to compute the orthogonal complement of a span. We just put these vectors as rows in an augmented matrix for a homogeneous system. Okay. Then once we have U1 through UM, we double check it's an orthonormal basis. Okay. It's possible when you compute this complement, you might get something that's not orthogonal. If it's not orthogonal, you have to make it orthogonal by using Gram-Schmidt and then normalizing it. Okay. But once we have our orthonormal U1 through UM, we set them as columns as U, and that will give our singular value decomposition. Okay, so this is our most complicated construction so far, and as usual, it'll be a bit clearer once we do an example. Okay, so here's an example of computing the singular value decomposition of a matrix. Okay, so this is question 7.49 in the book. So I want to find the SVD of this matrix. Okay, just by inspection, we can tell it's a rank 2 matrix because the 2 column vectors, one is not a multiple of the other. So how we start is we look at A transpose A, and we orthogonally diagonalize it. Okay, so you should find that the eigenvalues of A transpose A, lambda 1 is 18, and lambda 2 is 2. And we want to order these in decreasing order. Okay. The associated normalized eigenvectors for these 2 eigenvalues, you can check, are written here. Okay. So that's the first step. We found our V's, and we have the information to find our sigmas from these 2. Okay. So we can form our matrix capital V just by taking the little v's, V1 and V2, as columns like this. Okay. Now, to compute our sigmas, right, we want to take the square roots of the eigenvalues of A transpose A, which are guaranteed to be positive or 0, since A is positive semi-definite. Okay, so sigma 1 is going to be the root of 18, sigma 2 is going to be the root of 2, and now we form our sigma matrix like this. So remember, if you're unsure about the size of the sigma matrix, just remember it has to be the same size as the original A. Okay. And so you just go along the diagonal of it, and you write on the singular values as they appear in decreasing order, like this. So you put root of 18 and the root of 2 there. So we have V and sigma. We just need U now. So we can find U1 and U2 by using the singular value relationship like this. So A times V1 equals sigma 1 times U1. Okay. Now, if I want to solve for U1, I can rearrange like this. Okay. I know sigma 1 is not 0, so this will work. And if you work it out, you get that U1 equals this. And then similarly, get the U2 equals this. These two are already normalized. Okay, so I don't need to normalize them. And they will always be orthogonal just by this construction. Okay, so not done yet, right? U is a 3 by 3 matrix, right? U has to be m by m, right? And we have 3 columns here. V is 2 by 2 because we have U has to be 3 by 3 because we have 3 rows. And V has to be 2 by 2 because we have 2 columns. M's and the V's. So U needs to be 3 by 3. So we need another U's 3. Okay? And we've run out of V's to get the U's, right? So how do we get it? Okay, like I said, what we want to do is take U1 and U2 and extend it so that we have U1, U2, U3 as an orthonormal basis for R3. So what we can do is compute the orthogonal complement of the span of the U1 and U2, which is equal to the column space of A. So we're computing the orthogonal complement of the column space of A. So how we do that is we take U1, U2, we write them as rows in the augmented matrix like this, and then we solve. So for this system, it's very easy. We get that U3 is going to be 0, 1, 0. Okay, and so our U matrix will be U1, U2, U3, and it forms this. So in total, this will be our singular value decomposition of our matrix here. Okay, our m by m, or our 3 by 3 U, our m by n, or 3 by 2 sigma, which is the same size of A, and our n by n V, which is the same, which is 2 by 2.